All right, now that we have a somewhat muddy idea of what a Riemann sum really is, let's figure out how to use them. So remember, we use Riemann sums basically to find the area under a curve of something that we couldn't find with an integral. So let's take a look at something like this, and let's just, before we do any of these problems, let's just kind of look and see what the different sums would look like. What are the different types of Riemann sums? Well, the first one is a right-hand Riemann sum. So a right-hand Riemann sum, remember, is I make rectangles, and I use the height of the right side of that rectangle to draw the actual rectangle. So in this case, we're going to do, let's just do 5 equal rectangles on this one. So we're going to do one every 2. And a right-hand Riemann sum would look like this, right? So that means I'm going to have a rectangle here, and I'm going to have a rectangle here, and I'm going to have one. Those are really beautiful brackets there. Here, I have a rectangle here, and I'm going to have a rectangle there, right? So those are my 5 rectangles, right? And so then I go to the right side of those rectangles. That would be right here. That would be the right side, right? If the rectangle is too wide, that's the right side of the rectangle. And I go all the way up to the curve, and I draw a rectangle that is the height of whatever it is there at the right side of my rectangle. Okay, so whatever the function value is at 2 is the height of my entire rectangle. Does that kind of make sense? I hope so. So then at 4, I'm going to go up to the function value at 4, and I'm going to draw a rectangle that's the height at 4. Okay, and then I'm going to go up to the function at 6, that's the right side of my rectangle, and I'm going to make a rectangle that's the height of that right side. And then at 8, I'm going to make a rectangle that's the height at 8. I'm going to make a rectangle that's the height at 10. So this is what a right-hand Riemann sum would look like. We would find the area of each one of these rectangles, and that would give us an approximation of the area under the curve. You can tell that this would not be a great approximation of this curve specifically. We'd be missing quite a bit and overestimating in some places and underestimating in others, and so that's why we have lots of different Riemann sums to use. So this is a right hand. Okay, let's look at what a left hand would look like. Actually, let's see if we can do it without it being too messy. A left hand, we would have 5 equal rectangles just like we wanted before, but what we're going to do is we're going to start, our rectangle is going to be the height of it on the left side. So in this case, the left side of the triangle, rectangle, I keep calling him a triangle. The left side of the rectangle is at 0, so the height of this one is 0. Okay, and then the second rectangle would be this one here. And then the third rectangle would be this one here. And then the fourth rectangle would be this one here. And then the fifth rectangle would be this one. So you see the green area is going to be a left-hand Riemann sum, because I went and I said, okay, here's the left side of the rectangle, and the whole rectangle is going to be the height of whatever it is, whatever the function value is on the left side of the rectangle, right? So I go up to the function value and I make that. Okay, so hopefully you can see that. And then this one would be like a gross underestimation, like by a long shot. You can see all of the stuff that it's like not estimating that it needs to. So then we also have the midpoint, and we're going to go ahead and erase for that one. So let's just draw a midpoint Riemann sum on this one. So the midpoint would say, all right, if I'm going to do 5 equal rectangles, that means that one rectangle goes from 0 to 2, right? Well, what's the midpoint of that rectangle? Well, it would be at 1, right? That's halfway in between. So I'm going to make my rectangle so that it's the same height as whatever the function is at the midpoint. Okay, so the function at the midpoint is at 2, so my rectangle is that rectangle. That's the rectangle that I'm going to use. Okay, so then the midpoint of the rectangle that's from 2 to 4 is 3, so that would be right here, right? That's the midpoint. And so I make the rectangle so it's the same height as the midpoint right there. Okay, and then here's my midpoint here. And I'm going to make a rectangle that's the same height as whatever the function is at the midpoint. And then this is the midpoint of this rectangle, so I'm going to make it there. I'm going to do the midpoint there. And so then this would be, if I found the area of each of these rectangles, this would be a midpoint Riemann sum. And that would give me an idea of the area under the curve. And you can see this one actually is a little bit better estimation. Actually, it looks to be better. And midpoints aren't always the best estimation. It really depends on your curve. So those three are the main three: the left, the right, and the midpoint. There are two other ones that we're going to look at. I don't see them as much, but they do cover them in our textbook, so I want to make sure that we're covering them. Especially because our textbook is written by an AP reader, so he understands things that we might need to understand better. So the one kind is an upper circumscribed Riemann sum. And an upper circumscribed Riemann sum means that the rectangle has the entire function, let's see, the entire function is underneath the rectangle. Okay, so I'm trying to find the exact right way to say that, but basically the entire function is enclosed underneath your rectangle. So we're going to do 5 equal rectangles again, and so that would mean that we'd have a rectangle like that goes from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. Okay, so we need to draw a rectangle that encloses every part of the function that's inside of that interval. Okay, so for this one we would draw this, and if we look, that's the highest point in the interval, so that's how tall our box is going to be. And then here on the 4, we couldn't stop right here because that doesn't enclose the entire part of the function, right? We need to go all the way up here so that it's actually, so that the function is, and that should be right on the function, not a little above, but you know how my straight lines are. The whole function is inside. Okay, and then this one, same thing. We couldn't stop right here because that wouldn't enclose the entire function. That rectangle now encloses the entire function. This one encloses the entire function, and that one encloses the entire function. So then this Riemann sum, the area of these rectangles, would give us an upper circumscribed Riemann sum. And then finally, the last one that we're going to see for now, let me make sure, yep, we're going to do trapezoidal next unit, but this unit, the last one we're going to see is a lower circumscribed one. So this is the idea is that, see, before the function was enclosed completely inside of the rectangles, and this time the rectangles are completely inside the function, meaning no rectangles go outside the function. None of them are taller than the function. And again, we're going to have 5 equal rectangles. So we're going to have one from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So let's figure out how tall can the first rectangle be if we don't want it to go outside the function. Well, it can't be tall at all. It has to be like 0, right? And then the second one, how tall can it be if we don't want it to go outside the function? Well, it can't go any higher than the lowest point. So that's the tallest rectangle we could possibly make that would give us, that would all stay inside the function, right? And then this one, same thing. Hi, buddy. Hi. My 10-year-old wants to learn calculus, so, you know, there's that. So that one's on the inside of the function, okay? And then this one could only go right up to here, you see, because if I went any higher than that, it would be outside the function. And then this one can only go to here because it would be inside the function. So this Riemann sum would be a lower circumscribed, or an inscribed, sorry, yeah, see, I knew I was right, an inscribed Riemann sum, and basically it's all inside, the rectangles are all inside the curve. So those are the 5 different types that we're going to see: left hand, right hand, midpoint, upper or circumscribed, and lower or inscribed.